And welcome everyone. Chongying is going to be talking about pointed modular categories. Feel free to start whenever you're ready.
Okay, and thank you for the invitation. Okay, the title of my talk is Pointed Modular Tensor Categories. This is a joint work with Richard Ying, a professor from Louisiana State University, and Li Ren, and a professor from Sichuan University in China. So in this talk, we are going to touch two subjects. One is so-called modular categories. And I think with modular categories, it has origin in the paper by these three Russian physicists, Belevin, Polyakov, Zamolodchikov in 1984. In this very famous paper, they first proposed so-called two-dimensional conformal field theory. Okay, and two-dimensional conformal field theory in physics, the whole theory was summarized by Mossberg in 1989. Okay, in 1989. This is basically including breeding matrix, fusion matrix, and then Turaf in 1991, I think basically collect all the data from Mossberg's paper to give a definition of so-called modular tensor category. Okay, modular tensor category. Okay, so the second one I'm going to talk about in this talk is so-called vertex. Oh, I think what's going on? Oh, okay. Is vertex operator algebras. Okay, and the vertex algebra was first introduced by Bocher in 1986. Then a special class of vertex algebra is so-called vertex operator algebra, was extensively studied by Frank Lepos-Merman, and according to them, this one is more, I think, close to so-called Carroll algebra in two-dimensional conformal field theory in physics. The connection is the birth of both modular tensor category, and vertex operator algebra were motivated by two-dimensional conformal field theory. Okay, so this is, of course, right now we know, and this two is something that inseparable. Okay, basically, if you want to start VOE, you need to know category theory, and also vertex operator algebra. The representation theory of vertex operator algebra provide a lot of good examples of modular tensor category and or fusion category. A second connection about the two different things is so-called reconstruction program. Namely, every modular tensor category can be realized as a module category of a rational vertex operator algebra. Okay, so this one I think has been studied more, I think, in a conformal setting. But this one, at this point, people believe this will be a true statement. Okay, but of course, at this point, it's just largely a conjecture. Okay, so here are just our main result is the first one is so-called every pointed modular category can be realized as a module category of lattice VOE. Okay, and the so-called pointed our mention just it's just every simple object is a simple current. Every simple object is invertible. Okay, this so-called if your module category, every simple object is invertible, or every simple object is a simple current, such category is called pointed. Okay, so in this case, it can be realized as a module category of lattice VOE. The second one is the module category of any pointed twisted drain field double can be realized as a module category of VLG. Here, VL lattice VOE, L is unimodular. G is because in the twisted drain field, when defined twisted drain field double, you need to find the group and a 3 co-cycle. Okay, this is the same gene can be realized as a VL as a fixed point VL. This one is this again is VOA. This in fact this is still lattice VOA and can be realized as a module category of holomorphic VOA VL. The module category, yeah, I just VLG. VL in fact is holomorphic VOA. G is the finite automorphism group of VL. Okay. Here, as mentioned, okay, VLG is a fixed point VL and this group G. The same G, any pointed twisted Dirichlet double. Twisted Dirichlet double means the corresponding module category is pointed, or you can just see twisted Dirichlet double is abelian, is commutative, Okay, it's equivalent to the statement twisted Dirichlet double is commutative as a associative algebra. Finally, I want to give a remark. The module category of any twisted Dirichlet double is a modular tensor category. Okay, so this is a fact. So in other words, you can. This is just like a part of this reconstruction program. If of course I think Terry Garland and Evans Garland they did more, but use this orbifold theory to realize the pointed. The module category of pointed twisted Dirichlet double is this is new. Okay. So first, I just see what is pointed modular tensor category. Okay, I just briefly define. I think people here are experts on category theory. Okay, and C is a modular tensor category. First, C is a semi-simple tensor category, okay, just with the tensor product. And okay, so we require this there are only finitely many equivalent simple objects, okay, and also the morphism space is a finite dimensional vector space. Okay, here we talk about category over C. Okay. We also have object one, okay, and also every object has a dual, okay, plus a lot of axiom, okay. I just don't want to, but most importantly, we want to have this so-called gradient, okay. We have this gradient. Gradient just is a morphism from object x tensor y to object y tensor x. It's a gradient, okay. Again, it satisfies certain axioms. Modularity, but here I just okay, but I didn't mention okay, but here you want to define the so-called trees, then you can define S matrix, T matrix, and but here I just want to see modularity. Just that in modular tensor category, the modular group acts on a gross Deakin range of this category, or you can call this fusion range because see you get a range, you have a simple objects, and you have a Z linear combination or C linear combination, and then you have natural fusion range. Okay, X up here. So in other words, module group at X on any simple object, as a linear combination of simple objects, So it's a module tensor category, but of course you can define so-called Milk center trivial and so on, and spherical. But I just said it's module group X up here because I really don't use how module group X on this category. Okay, then I just okay. A modular tensor category is pointed if the simple objects forms an abelian group and their tensor product. In other words, if x, y are simple objects, x tensor y again a simple object. So in other words, the equivalence class of simple objects and their tensor product with unit one is a group. Okay, so this is a group. This is just what we just mentioned. Then I just want to say, okay, recall a vertex operator algebra is called a rational if the module category is semi-simple. But here a module category is I just vague. Okay, it's just a Z plus graded module category is semi-simple, okay? And again, because another concept we have to use is a VOV is called a C2 cofactor if subspace C2V, which is spanned by U negative 2 X on V for all UV in V, if this subspace has 5 codimension. And in this case, VOV is called C2 covariant. Okay, these two concepts, both concepts are important. Okay, first concept is this just a general in representation theory. If you the first thing you want to know this category is semi-simple, a representation category is semi-simple. Second concept is it's kind of artificial, but this in original paper of Zhu, this condition guarantees the formal trace function in the representation in the representation theory converges to holomorphic functions in half plane. Right now, I think almost all good results require both rationality and C2 covariance. In particular, when dealing with the modular tensor category coming from a vertex orbit algebra. Here is this result by Huang that if V is rational C2 covariant, of course, you also need to have VO is self-reduced, but I just majorly, there is two assumptions. V is rational and C2 covariant, then V module category CV is a modular tensor category. Okay, so this is a result of Huang. Now I just recall lattice VOE associated to a positive definite even lattice error. First, the error is a free abelian group of finite rank, and also there is a positive definite z-valued bilinear form. Okay, and even means alpha just the alpha inner product equal to is a even integer. Okay, for any alpha. I just want to use this VL. This just equal to symmetric algebra tensor CL. Okay, tensor CL. This symmetric algebra, this just L is an abelian group, so it's a Z module. I just change coefficients from Z to L. Namely, I consider C tensor L over Z become complex vector space. Then you just extend, this bilinear form by C linearity to get a vector space with a bilinear form. Then you get graded symmetric graded vector space. Then get a symmetric algebra. Okay. VL here I use group algebra. In fact, really it's twisted group algebra, but I just gonna. Okay, I think this one is then we have this dual lattice. Dual lattice is just you consider all beta in this vector space such that beta L inner product in Z, and it's well known. And L0 again is a dual lattice, again is a free abelian group. The quotient is a finite abelian group. Okay. Here I just want to mention. Okay. And okay, by the way, I say for lattice view, I want to mention more. I remember. Okay, this one this was a long time ago. I had a long conversation with Boucher, because when he first give definition vertex algebra, I was very curious. I just asked him how he found this axiom. Of course, he told me. Of course, originally this vector space for L is an AD type root lattice. This one was used so-called Fock space or in physics and was used by Frankel, Katz, and Graham-Sigel to construct so-called basic representations of alpha and Katz-Moon algebra. Okay, of AD type. Boucher said, what happens, even of course when Frankel Katz they consider representations for alpha and Katz-Moon algebra, they only consider alpha has a square length, alpha inner product 2. Boucher, the naive question is what happens if alpha is an arbitrary element in lattice And you just use the same definition vertex operator without any change. You want to know what's the identity this operator satisfy, what's the identity this operator satisfy. He told me he just had more than 100 pages of, I think, calculation. He found this so-called this Borch's identity, or right now you call it Jacobi identity, and so on. But he said he must be right identity. This how he told me this identity, how this identity come from. This who just come from calculation of these operators y, alpha, z. If alpha not a root, in general, of course alpha root, you have this so-called basic realization of alpha and custom-model algebras. But of course he was interested more in the case one error Lisch lattice, because this has something to do. Of course, right now we know this has a relation with a master simple group and a moonshine phenomenon. Okay, so here I want to mention this one, this result. Okay, and me, and also I should mention also this. I forgot to write a name, and my joint work with Haisheng Li and Jeff Mason, and also with Lepowski. This in this book is so-called relative vertex operators, and this paper, and this VL is rational VOA, and the irreducible simple the irreducible model exactly this VL plus lambda. VL plus lambda is the so-called coset. Is just the coset of error in dual-lattice error 0. Okay, this coset. Okay, CVL is a pointed module category, and the irreducible CVL just exactly as morphic to error 0 over error. We know mentioned this. Of course, this in fact this view is rational and a C2. So module category is a module tensor category. But when we wrote this book, we didn't know module tensor category. But the information we given there just tell you this one is a pointed module category. Of course, everyone's simple current, irreducible module is just this one. In fact, in this book, we just mentioned we also use so-called abelian 3 co-cycles and so on, gradient and fusion. We use this one, and also we just collect all this one. We get a so-called abelian 20 algebras. In fact, later on we just mentioned you have simple object, you have VOA, and if every object is simple object is a simple current, you consider this direct sum of all these simple objects, you get a so-called abelian 20 algebra. Okay. So here you give a pointed module tensor category, we can get an abelian group. A naive question is, given an abelian group, can we get a pointed module tensor category? The answer is partially right, partially wrong. Okay, so given an abelian group, can we get a module tensor category? But the answer is no. For arbitrary abelian group, we need a so-called quadratic form. Okay, suppose G is abelian group. A is a function, a function Q from G to unit circle S1 is called a quadratic form if first QA equal to QA inverse for any A and G. Second, you can define so-called in linear algebra called bilinear form, but here we call it back character because we use multiplication in G. Okay. Bxy equal to Qxy over Qy is a back character in a sense. If you fix X, you vary Y, you get a character of G. Similarly, if you fix Y, you let X vary, you get a character. Okay, it's back character. Q called non-degenerate if B is non-degenerate. Non-degenerate means if fix X, if Bxy equal to 1 for every Y, X must equal to 1. Similarly for the Y, okay, so it's non-degenerate. Okay, so you have this we have so-called non-degenerate quadratic form. Okay, so here is a result that if C is pointed, then you define Qx is a gradient. We just mentioned, okay, gradient, you have X tensor X to X tensor X. You take this gradient. This one give you a quadratic form from this abelian group. This abelian group, of course, consists of simple objects of category to S1. This is a non-degenerate quadratic form. Conversely, if you have a abelian group, finite abelian group with a non-degenerate quadratic form Q, then there is a pointed modular category denoted by C cube G, such that the equivalence class of simple objects of this pointed modular category is exactly the abelian group we started with. Okay, and the CXX, this breeding CXX, exactly is a quadratic form Q given by this QX. Okay, so in other words, a pointed modular category equivalent to a finite abelian group with a non-degenerate quadratic form. Okay, so this, okay, back to, I think, Annenberg, McLean in 1953-54, but in the modern language of modular tensor category, this is given by Etnikov, Niksic, Galaki, Ostrich in 2015. And in fact, I just want to mention, okay, and this one, of course, basically uses abelian three cosec, but as I mentioned, one Lepowski and I, we wrote this book, we didn't know any modular category. But basically, this one is this breeding and Orsin we have in the paper already. Where but back then we just didn't know this modular tensor category. Okay. And also, I just want to mention, if you have a pointed modular tensor category, you just direct sum of all these simple objects. Okay, then it forms a abelian 20 algebra. Okay, use language in a book by Lepowski and myself. Okay, so here I just want to mention this is a result. Okay, which says if C is a pointed modular category, then there is this pointed definite even lattice L such that C equivalent, this is called a braided equivalent to CVL. Okay. In other words, the irreducible object of C, this abelian group is isomorphic to dual lattice of L over L. We mentioned already this reconstruction program holds for pointed modular tensor category. Okay, every pointed modular tensor category can be realized as a lattice, as modular category of lattice VOE, namely a modular category of a rational vertex orbital algebra. Okay, now let's just go to the second part of my talk, so-called pointed twisted Dirichlet double. Pointed twisted Dirichlet double. So here we just, of course, also discuss its connection with the holomorphic orbifold theory, First, let's just recall this two called twisted Dirichlet double d alpha G. Okay, suppose G is finite group. Alpha is a 3 cocycle of G with coefficients in S1. Okay, then twisted Dirichlet double is just as vector space is CG star is dual. Okay, it's dual space tensor CG. Original twisted Dirichlet double is a Hopf algebra tensor is dual, but of course we know for group CG's Hopf algebra, this you can use the original twisted Dirichlet double. Okay, then I use this notation. CG, we know group algebra has a basis consists of group elements. Okay, and then we also have a dual basis delta G, which x on x equal delta gx. In other words, if gx equal to 1, otherwise equal to 0, this is dual basis of x. Okay, this is just twisted. This is just we use this. It's called dual space with this distinguished basis. Then the twisted Dirichlet double has a basis delta G tensor x. This notation I used from this was G graph Pasquier Rocher. in 1990. Okay, from their paper. Okay, this is also twisted drift double. This concept also come from their paper. Okay, so we use this notation. This G, this notation Gx, this equal delta Gx for this basis element G delta G tensor X. Then you have this how we define the product Gx_Hy equal delta Gx_Hx inverse Gxy. This theta Gxy, our mentioned, I will just give you how theta G is defined. Similarly, you can define co-product in this one. Okay, you have a co-product. Okay, delta Gx. This is just how we define co-product. Okay, again, gamma x also is defined in terms of alpha. This 3 cosec alpha. Okay, if this 3 cosec equal to 1, both theta G and gamma is trivial. So it's original Drinfeld double. And so this is the theta G and gamma theta and the definition theta gamma. Okay, theta gamma. This is a result of so-called D-graph particle rupture in 1990. Okay, and basically the result says d alpha G is a. I use this. Okay, I use C d alpha G for the module category of d alpha G. Their theorem says the module category d alpha G is a modular tensor category. But of course, I should I'm cheating a little bit because back then there are no definition modular tensor category. Using that, but they got all information you need to claim this module category is a module tensor category. Because module tensor category's concept was proposed in 1991. But back then, they give you all Brady metric, fusion metrics, and so on. But the information they obtained can guarantee this DRPG module category indeed is a module tensor category. In this one, they call this one called twisted Drinfeld double. Okay, twisted Drinfeld double. But why DRPG? Normally, I think this should be. I think people who are working on Hopper algebra should be more interested in this kind of thing. They don't want to construct more kind of twisted, more new examples of Hopper algebra. But this is so-called quasi. This in fact is a quasi-triangular Hopper algebra. You have this so-called R matrix. But okay. But the point is, the question is why dr by G? The answer is holomorphic obfuscation theory. Okay. Holomorphic obfuscation theory. Okay. So basically, they want to use this dr by G twisted Drinfeld double to understand so-called holomorphic obfuscation theory. Okay. Now let's just mention. Okay, right now people also know what is obfuscation theory. Okay, so-called obfuscation theory. Suppose V is vertex operator algebra, G is a finite automorphism group of V. Then V fixed point again is a vertex operator algebra. We want to know how to use V and G to understand the VG and the VG module category CVG. Okay, so this is the question about obfuscation theory. Okay, we understand the VG module category. Okay, so here I just want to see. Okay, what is obfuscation theory conjecture? Okay, if V is rational and G is finite group, then VG is fixed point is rational. Second one, I said every irreducible VG module should occur in a irreducible G twisted V module for some G in G. According to, I think this one, according to Mohr-Sandberg's paper, okay, and also I think influenced by Wheaton. Basically, they just I like this conjecture that every rational VOE should come from this lattice VOE, versor VOE, and alpha VOE by orbifold construction, coset construction, and extensions. Okay, this basically you perform this one, you should get again get rational VOEs. But the problem is in VO theory, in orbifold theory, we don't know the first part. If it's rational, of course we believe this is true, and but of course we don't know if this is true in general. Okay. And then the progress, if G is solvable, then of course this Miyamoto, Callahan, they prove this is the conjecture part one. But in fact, they prove is G is cyclic. But it's very easy to conclude if G is solvable, then and VG is rational. If V is rational, of course. But here I assume not complete. In fact, you also need to V is C2 cofinite. The regularity. If V is regular, then you prove G. VG is regular. If G is finite group, okay. This is what they proved. Okay, but here I just forgot about C2 cofinates. And by the way, we also know, and in VO theory, people believe rationality implies C2 cofinates. Okay, even we cannot prove it, but we believe it. So from this point of view, so rationality is a real assumption. Okay, is a real assumption. And then in joint work with Ren and Li Ren and Feng Xu, we prove, yeah, it's true. If you assume VG is rational, it's not very hard to prove. And every irreducible VG module occurs in a irreducible G-twisted V module. Okay. And by the way, I think the difficult part to study orbifold theory is we don't know. We know how many twisted modules we know. Okay, but the problem we don't know how to construct twisted modules. I think this is a big challenge in studying orbifold theory. Okay, we don't know how to construct it. A view is called a holomorphic if V is rational and the only irreducible V module is itself. The adjunct repetition is irreducible. It's the only irreducible module. Such view is called a holomorphic. As I mentioned, orbifold theory need to understand the VG module category. This is called a G-graph Pascal-Roche conjecture 1990. This is our conjecture or their idea. You can see this basically the motivation for them to induce so-called twisted twin field double. Okay, this says if it's holomorphic, then for a G, okay, if it's holomorphic, then there is this G. I should say if it's holomorphic, G is a finite automorphism group of G. Then there is this some 3 co-cycle with coefficient S1 such that the VG module category equivalent to module category of twisted twin field double D alpha G. This is our conjecture, or this is our conjecture. This also there are motivation for introducing twisted twin field double. The reason why they study twisted twin field double. Okay, so here I give a remark. Okay, if L is unimodular or self-dual, then VL is holomorphic. If L is unimodular or called self-dual, then VL is holomorphic. Okay, and then in the same paper with Richard N and Li Ren, we prove and the D-graph Pascal-Roche conjecture is true under the assumption and the VG is regular. If VG is regular, we under this assumption. Okay, under this assumption. Okay. But here I just want to mention, okay, this result doesn't tell us if you have a given a 3 co-cycle, is there a holomorphic VOV such that G is a automorphism group V and the CVG, the VG module category equivalent to the module category of twist joint field double. So we only go to one direction. Okay, one direction. Okay, with only one direction. But for the reconstruction program, we need to know the opposite direction. Namely, for every alpha in for every 3 co-cycle, either holomorphic V over V and G is a finite automorphism group of V, such that and these two categories are equivalent. Here, I just want to mention, and the dr by G is called pointed if this module category, if the module category dr of dr of G is pointed. We just mentioned the module category is called pointed. Okay, and also this equivalent to dr by G is a commutative solution algebra. Okay, equivalent to any dimension, any representation in one dimension. In fact, okay. So here I just okay. This we said okay. If dr of G is pointed for reconstruction problem, as just mentioned above, but we don't know for any G. But if dr by G is pointed, then there is this unimodular lattice L such that G is the automorphism group of V, VL, and the VLG module category and the dr by G module category are equivalent. If this twist joint field double is pointed. And Garland and also Evans and Garland, they proved in 2018, this proof, okay, if for any finite group G and alpha is 3 co-cycle, there is this reaction V over V such that CVG, this V module category equivalent to module category twist joint field double. Okay, but this one from reconstruction program is a highly non-trivial result. Okay, basically you so-called permutation orbifol. You can embed this G finite group to any permutation group to Sn. Okay, they use this idea, but their result had nothing to do with so-called orbifol theory. We don't know you can realize this V as some UG. Use holomorphic VOA, G is the automorphic group. So from reconstruction program, this is a highly non-trivial result. We just expect we totally believe for every alpha in H3GS1 there is this holomorphic VOV such that of course and VG module category equivalent to dr by G category. We can prove this for a lot of examples. But for pointing, we can do this uniformly. But you can also, or for G, if G is the dihedral group or other group, you can do it. But for arbitrary group, we don't have a result. But if for any alpha, you can find a holomorphic VOA such that this conjecture is true. Okay, basically that's all my talk. Thank you very much for your attention.
Thank you so much. If you have a question, please feel free to unmute yourself and go for it.
By the way, I'm sorry, I didn't give details. I think this was talk I gave somewhere else, but I'm not very good at doing PPT. I just handwriting, so I was lazy. I should give more details. But people can ask me any question. If just ask question.
I think this is great. So could you say a little more about for which groups you were able to prove this conjecture that's here at the end?
I think for dihedral group we should be able to do it. This is just because dihedral group is not abelian, so it's dr by G not abelian. But even G is abelian, but dr by G maybe not abelian. dr may be not commutative. But for dihedral group, not definitely not pointed. Because repetition has some repetition dimension, not one. But in general, we don't know how to do it.
Thanks. Are there any questions? If not, let's thank Chongying again. Thank you so much for waking up super early
Thank you very much.
to keep the talk. Yeah.
Okay, thanks everyone for coming.
Okay, thank you so much.
Okay.
I hope to see you all next Thursday for our last talk. Thank you so much, Professor Dong.
Thank you. Okay.
Have a great week. Bye bye.
Yeah, have a nice weekend. Okay, bye bye.